Hello, welcome everyone. Today it's my pleasure to welcome Professor Katerina Chatziioannou from Caltech. Katerina is a specialist in gravitational waves. She received her bachelor's in physics from the University of Athens, then went to Montana State for a PhD, and actually was a postdoctoral fellow here at CETA. Before going to the Flatiron Institute in New York, after which she joined the faculty at Caltech. And Katerina is also a member of the Simons collaboration in extreme electrodynamics of compact sources, of which I am a member too. So we talk together about neutron stars, but about very different aspects. And today, Katerina will tell you about a decade of black hole observations with gravitational waves. Thank you, Katerina.
Great to be back after I was a CETA fellow between 2016 and 2018. So it's great to be back. I took a long walk yesterday, lots of familiar places. The view of the CN Tower through the clouds never gets old. Okay, so my research is on gravitational waves, and today I will tell you about some things that we're learning with gravitational waves about the properties of black holes. And gravitational wave observations are essentially a means to study the universe, same way we use electromagnetic waves to study the universe. So this is the gravitational wave spectrum. Same way with electromagnetic waves, we have different sources emitting at different frequencies. The example of sources are at the top. Then we build different types of telescopes at the bottom to target those different frequencies. The same thing exactly happens with gravitational waves, different types of telescopes for different types of sources. Now, there is a lot of progress in the last 10 years in almost all of these frequencies and almost all these observational efforts. I don't have time to go through everything. What I will be talking about today is what happens at the right side of this plot, the ground interferometers, the ground-based detectors that are detecting compact objects. These are mergers of black holes and neutron stars. So the detector here is mostly the twin LIGO detectors. These are the most sensitive gravitational wave detectors that we have to date. On the left is the LIGO detector in Hanford, and on the right is the LIGO detector in Livingston, Louisiana. And you see sort of very different locations. One is in the middle of basically a nuclear waste site. The other is in the middle of a swamp. But you need those detectors to be sort of isolated. You can't build it in downtown Toronto and expect to detect gravitational waves. You need to put them in the middle of nowhere. Okay, so gravitational waves famously were detected by LIGO 10 years ago. And that 2015, 2016, when I joined CETA, there was a very active gravitational waves group, which sort of went into a quite transition stage and completely revamped itself today with Maya and Reed here. So I think you've had a lot of gravitational wave talks, and it's a topic that's familiar to U of T. However, just to be on the same page, I'll give you the brief one-slide introduction of what are gravitational waves. So the kind of public talk introduction to gravitational waves says that they're ripples in space-time. I have no idea what that means. I never understood that. What gravitational waves are waves. If you take Einstein's equations that describe gravity and you massage them in a certain way, you get out a wave equation where h here is essentially the gravitational field, the gravitational metric, and it gets sourced by something. It's a wave in every sense of the world, same way you know about electromagnetic waves. They're sourced by changing quadrupole moments. So electromagnetic waves are sourced by dipole moments. Here we have quadrupole moments, something a little bit more complex because gravity is complicated. And like any wave, they go as 1 over the distance to the source. If you have black holes that are of mass m and are moving at some velocity v, the waves they are creating, the waves that we're detecting, have an amplitude of about 10 to the minus 21. This is a dimensionless number, no units, so take it as is, 10 to the minus 21, they're tiny. And their spectrum, how to understand the frequencies they're emitting, is basically Kepler's law. So the frequency that at which gravitational waves are emitted is roughly 1/the mass of the black holes that create them. So the more massive black holes create gravitational waves of lower frequency, which determines what kind of black holes you can detect with each type of detector. When two black holes collide, like the collisions we'll be talking about, you get a huge amount of energy emitted, the events that we're detecting are emitting a few times the mass of the sun in energy, gets released and travels throughout space for us to capture in our detectors. And in terms of luminosity, it's actually a staggering number. Luminosity is energy divided by time. So at the peak, at the moment the two black holes colliding, the luminosity of those waves is 10 to the 56, which is basically more luminous than the entire rest of the universe, which is at the same time a quite impressive fact, and also a bit embarrassing because it means that the most bright thing in the universe, we were only able to detect it 10 years ago. It's because their gravitational waves don't really interact with much. Okay, so since the first detection, of course, lots has happened. The schematic here shows you the detections we have made with LIGO as of today. So the y-axis is the mass in units of solar masses. The x-axis is time, basically human time, your time, the order in which we're making the detections. So each of these, say, clusters here is 3 objects. What this means is these 2 objects were in a binary, they merged with each other and gave rise to a final object after they collided. And this whole process emitted gravitational waves. So each of these cluster of 3 objects is one signal that we are detecting with the LIGO detectors. In blue, we have black holes. In orange, we have neutron stars. And you see from the masses here, these are neutron stars, the orange. We started very strongly in neutron stars down here. When I was at CETA, we actually got this one. I was a postdoc at CETA when this one happened. It was the first neutron star binary detection. It was also detected electromagnetically. It was a massive thing. A lot of the analysis for this event happened here when I was a postdoc. Lots of hours on the 15th floor here of the working on this. And since then, we've observed a few more neutron stars. We can use them to understand the properties of neutron stars, but you might notice a gap over there to the right. We haven't gotten as many neutron stars as we were hoping to begin with. Most of what we're detecting with LIGO today is black holes. So instead of neutron stars, which is what I did mostly when I was a postdoc at CETA, today we'll be talking about the black holes, because this is where our data are today. Okay, so let's see what we've been detecting, mostly black holes. The plot here on the x-axis is again time, but time scaled in your normal units. This is 18 weeks of observation, 38 weeks of observation. So it's proportional to your normal human time. And the different colors show you the different runs. So the different observing campaigns of the detectors. So the detectors go through these cycles of observing, shutting down to improve, observing, shutting down to improve. And every time they come back online, as you transition between the different runs, hopefully the detectors are more sensitive, which allow us to see more signals. The y-axis is going to be the distance, how far away the sources are. So the first run back in 2015, we observed 3 sources. The dots here, each dot now is not a black hole. Each dot is a gravitational wave. This is constellation of three objects from the previous slide. The color tells you how strong the signal is, and the size of the circle tells you the mass of the black hole. So we detected 3 back in 2015. The detectors came back online better, detected many more. The detector shut down, came back online, detected many, many more. The detector shut down, came back online, even better, detected many, many more. So the detectors are getting better. We're seeing these sources further out in the universe. And also we're seeing a lot more of them. The frequency with which we're observing them is higher because the detectors are better. Out here, we're observing about 1 event per month. Here, we're observing 1 every 3 days. This is a 10 times higher rate. This is because of this cycle of improvement, commissioning, improvement in the detectors coming back online that allow us to observe those signals to larger magnitudes. Okay, So we have those signals. What do they mean? Let's take a second to understand what we measure from those signals. The plot on the left is a gravitational wave signal, a typical gravitational wave signal, like any wave, it oscillates. And on the right is going to be a numerical simulation of two black holes merging that is about to start now. So early on in what we're observing, you have two black holes that are spiraling towards each other. They lose energy to gravitational waves, so they're getting closer and closer together. The frequency of the wave increases. So from this frequency evolution, we measure the masses and spins of the black holes, roughly. And from the size of the wave, we measure the distance to the source. Eventually, the black holes lose enough energy that they're getting very close together, and they are merging. The simulation will slow down so we can enjoy this stage as the two black holes are very close, they're wobbling, they're merging. And you have a final black hole that settles down by emitting any additional radiation it has, any additional perturbation it has from what just happened to it. Okay, so this is roughly the signal. And we are measuring at this point hundreds, dozens, a few hundred detections. And we're trying to analyze the properties, get an idea of what the properties of those sources are. Now, there's two kind of, first of all, I'm going to start by giving you a very brief overview of what the general properties of those signals are. This is not going to be the focus of my talk. The group here specializes in doing this kind of analysis. However, I want to very briefly mention some of the ensemble properties of the black holes, mostly for context for what happens later. So these is the black hole observations. The main thing that we measure is the mass of the black hole. And once we measure the mass of the black hole, we can start looking at what the black holes in the universe look like, what masses they have. The distribution here shows you what those masses are. If you look at the x-axis, we're talking about black holes of mass 10, 20, 30, 40 solar masses. These are sort of the black holes that we are detecting. Now, in this figure, I also want to show you the comparison between the white and the blue lines. The white lines are what you get with 70 detections back in 2020. The blue lines is what you get with 160 detections in now, 2025. So this again gives you an idea for the progress in the field. In 5 years, you've doubled how many signals you have. All your uncertainties go down from the white to the blue. So these are the masses that we are seeing more or less of our black holes. And there's a lot of astrophysics to do with curves like this. So there's a lot of work trying to understand, all the features you're identifying. What is happening here? There seems to be an overdensity, a lot of black holes here, a lot of black holes here, 10 solar masses. What happens at the higher end? How high do black holes get? All of these are astrophysics questions about where those black holes are coming from that we want to understand. However, this is not the focus of my talk. I mostly want to show this to give you a rough idea of what we're getting about the demographics of the black holes that we're observing. Mass is about 10, 30, 40 solar masses, a lot of work to understand the astrophysical implications of these detections. Okay, the other property of black holes that is interesting is the spin. Like any other objects, black holes also spin, though black hole spin is a kind of unique type of phenomenon. And the plot here shows you the measurement of the spin magnitude of the black hole. Spins are vectors, they have a magnitude and a direction. Here is the spin magnitude. In white, again, you have measurement from 5 years ago with 70 detections. And with purple, you have measurements today and purple and orange, you have measurements today from 160 detections. Ignore the difference between the purple and the orange, is not important for our discussions. However, what is important for us, for what we want to talk about today, is the rough properties of this distribution. So what we're learning about the spins of black holes out there in the universe. And black holes are definitely spinning. They're not all zero. That's good. If they were all zero, they would be kind of boring. So they have some spin that we can measure. However, the spins are also not large. One here is the largest spin magnitude black holes can have in general relativity. That's an absolute bound from general relativity. And they don't have very large spins, the black holes we're observing. Instead, most of them have moderate spins around 0.2, which means 0.2 means 20% of the maximum spin they could potentially have. But most of them are low. Our black holes are not, most of them are not spinning very fast. So these are the main things that I want to take away from the last two slides. Black holes have masses 10, 30, 40 solar masses, small-ish spins. This is what the majority of them have. Chris, you have a question?
New data set. How many sources are really contributing to that signal?
Yes. So these events are rare, but there are some. So the Chris question is how many of them? I want to specifically talk about one of them. On the question of how many, the answer is something like 3 to 4 have. It depends on whether you mean something that has support up there or something that needs to be up there. A lot of them are uninformative and have support in this range, but the ones that really want high spins are only a handful. And one of them I want to explicitly talk about because it's an outlier. This is why I'm showing you this for context for something that does not belong in this picture for what most of them are looking like. And the first event I want to talk about is something called 231123. This comes from when it was detected. It was detected in 2023 on the 11th month on the 23rd day. 11th month means November. And what is unique about this, there's two things that are unique about it. First of all, it's extremely heavy. Its total mass, the sum of two masses, is 240 solar masses, way higher than the 30 solar mass black holes that we're mostly detecting, right? So already, this is a unique event. The uniqueness, you can sort of see it here. This is the data as a function of time in the Hanford detector. And this is the signal that we're detecting. If you look at all the wiggles in the signal, it doesn't look like the nice long signal of inspired black holes I was starting with. Instead, we're not seeing the two black holes inspiraling. What we're seeing is just the two black holes merging. This is a fairly low frequency signal. You can count by eye the cycles and count the frequency yourselves. But because it's short, it means we only see the merger, which means it's very high mass. The other thing that is unique is exactly the spin. So this plot here is kind of complicated, but what it basically tells you is that the black holes have large spin. The zero, if your measurement is here at the center, the black hole spin would be 0, but your measurement is out there, which means the black hole spin is large. So these black holes, this signal, this black hole merger was unique because it had both high mass and very high spin. This is not typical. This is not your typical signal. What complicates things is that when you have these very short signals, when you just view the merger of the two black holes, it is harder to analyze it. Gravitational wave analysis is unique in general astrophysics in that when you have two black holes merging within general relativity, if we believe general relativity, that we can describe the system perfectly. We don't have any missing physics. We don't have any plasma running around and we don't know what it does. However, still, when you have two black holes merging, you can only solve for this problem numerically. You get out the exact answer for what the signal looks like, but it's still a numerical solution that comes out. It doesn't immediately tell you this part of the black hole gives you this part of the signal. You don't immediately know what is going on. So sometimes this creates problems in the sense that our models give different answers about the properties of the black hole. So the plot here shows you the total mass of the binary. This is, if you take the two black holes and sum them, get the total mass and the mass ratio of the binary. And the different colors give you results for the properties of this event under different models. The different model names are here. If the model names mean nothing to you, amazing, don't worry about it. If the models mean something to you, I'm so sorry. However, these are different models that try to capture the same physics we understand from numerical simulations, but are trying to capture them. And you see that they kind of disagree. They give you different answers. Look at the dotted lines for the event itself. They give you different answers, however, not too different. It's still very massive. The mass is really large. However, the mass ratio is hard to measure. However, because we can understand those signals from our numerical simulations in general relativity, what we can also do is try to understand where those systematic kind of differences are coming from. And this is the solid lines. The solid lines are our best attempt to reproduce those systematic differences because we understand how those models behave, we understand how the detector operates, we can fully reproduce those problems, those systematics, and understand where they're coming from. So in these very massive systems, the systems that are different than most of our populations, we will have problems in the analysis, we will have systematics. But for the most part, because our models are tractable, the physics in our models is tractable, we can reproduce these issues and be confident that, okay, if I can reproduce these issues here, the issues that I see in the real data, I have a better handle of what could have gone wrong in the data. So when you're seeing these very high massive sources coming out of LIGO, they're going to be challenging for us to analyze. However, I am confident that it is doable. There was a question. Yes.
What differentiates the models?
You want to know the difference between the models?
I mean, also what kind of numerical schemes, like what kind of simulations are these?
Yeah. So the numerical simulations are basically they're solving the same equations. You have the equations of general relativity and you solve them. There are different numerical schemes to solve them. Some basically they fall into the categories of finite differencing versus spectral methods. When I was a postdoc here, Harold Pfeiffer, for those who were also around 2015, was an expert on the spectral methods, which are probably that code is to this day the most accurate and faster code. Now, these simulations are also very slow. They would take weeks. So what these models do are basically different attempts to emulate the simulations, either by just using the numerical simulations or by also trying to incorporate some physics, some analytical modeling. So this is what the different names mean. Does that answer your question?
Yeah, we can talk about it.
Okay, I'll be happy to talk more about this. Okay, so this is one event that is very different than most of the black holes that we're detecting. That is challenging to understand. However, I think that the differences are tractable, as we're finding here. We can reproduce what seems to be going wrong with it. So we are still confident in the big picture conclusions. This is a very massive event. The mass is very high. The spin is very high. It's still very exciting. Okay, so that was one unique event that was worth spending a few minutes on. There's one more event I want to talk about for the rest of this talk, and it's the following. You might have noticed that there's a large black region at the end of this plot. If we look at what happens at the right side, you have something like this. We were observing during this time, and we have a lot of detections. However, the circles that represent these detections here are not fully analyzed and released. That's why the circles, for the most part, do not have colors and sizes. They exist. The data is in the can, and we will be sharing them soon. However, there is one circle out here that this is what I want to talk about for the rest of this talk. And what is unique about this circle is its color. Color means signal strength. It means that this signal was extremely loud. So let's see what happens when you get an extremely loud signal like this. So this was called 250114 because it was detected on January 14, 2025, about a year ago. And the plot here shows you the data in the Hanford detector on the left and the Livingston detector on the right. At the bottom, you have a spectrogram, which is basically a time frequency decomposition of the signal. You get this nice pattern of increasing frequency with time as the black holes come together and merge. Okay, so this was a very loud signal. What happened? Why was it so loud? So let's take a step back in time and connect this to what was happening at the detector 10 years ago. About 10 years ago, the Hanford detector recorded this signal. This was GW150914, the very first detection of gravitational waves ever. And if you quantify something like the signal to noise ratio, the weird way we define it, you get a number of 26. The green here is the gravitational wave signal, and that is on top of the purple. The purple is the noise in your detector. So the detector had some noise. On top of this, you have a signal. You record this. 10 years later, or something later, the detector records this. This has a signal to noise ratio of 80. This is why it's so loud. The green here again is the signal. The signal is not that different from 10 years ago. It's It may be a little bit louder, but not that much louder. What really changed in the last 10 years is the purple, is the noise in the detectors. The noise in the detectors went down by such a large factor that allow us to record the same signal and hear it much, much more clearly. So 10 years later, we got something that is a very similar signal, but because the detectors were so much better, it really allows us to track the progress in the field in the last 10 years. So if we look at this signal, it's actually very similar to the first one, like we were seeing in the previous plot, in the previous schematic. The plot here shows you the masses. M1 and M2 are the masses of the two black holes. And you see that the new one is consistent with the old one, but much better measured. And some of the numbers on the right show you its properties. The mass is about 60 times the mass of the sun. Mass ratio consistent with 1. No spin. Remember, most black holes have low spins. No eccentricity, no spin precession. Final mass about 62 solar masses. Final spin about 68% of the maximum. This is what we would call a vanilla black hole. It looks very similar to the other black hole detections we have observed so far. You're not going to get a lot of interesting astrophysics out of it because it looks very similar to a lot of other signals we have seen. What you can do with it instead is get some very nice tests of the fundamental properties of black holes. Because the signal is so strong, you can have a very clear view of the merger process of two black holes in a binary. So then with this signal, we can do specifically 2 tests of the fundamental properties of black holes. The first one is basically we can look at the ringing of black holes. What that means is if you have 2 black holes merging, they merge somewhere here, then you have one final black hole that sort of stabilizes by emitting any residual radiation it has before it settles into a Kerr black hole. So the final stage at the very end where the signal has died out is a standard Kerr black hole of general relativity. So the way to understand this part, this ringing, is through perturbation theory. You have a Kerr spacetime at the end, and as you go backwards in time, you start adding perturbations to your system, and you do perturbation theory, and specifically first order perturbation theory, same way you typically do first order perturbation theory, but in this time about the Kerr spacetime. When you do that, when you do perturbation theory, the answer that comes out is quasinormal modes. So these are quasinormal modes have a pattern like this. They are essentially a damped sinusoid, like most quasinormal modes. And they are characterized by specific indices, L, M, and N in this case, that I'll talk about a little bit more. So the quasinormal modes have some amplitude and phase that's determined by the initial conditions. Basically, how the black holes merged determines which modes get excited. But they also have a frequency and a damping time that does not depend on the initial conditions. It only depends on the Kerr spacetime that you're talking about. If you have a specific Kerr spacetime, it will unambiguously tell you what kind of modes you can possibly excite it, what frequencies and damping rates they will have. So let's look at an example of what those frequencies and damping rates are. The x-axis is the frequency, the y-axis is the damping rate, and this shows you results for a black hole of spin 0.68, so consistent with the black hole that we detected. Most of the radiation comes out in the L equals 2, M equals 2 mode. Ignore the N index for now. L and M are your standard angular pattern indices. And because of the geometry of the system, it's a quadrupolar system, quadrupolar theory, most of the radiation comes out at L equals 2, M equals 2. Then as you change L, you get different frequencies for modes, or if you change M, you get different frequencies out here. What is more important for our purposes is not L and M, is actually N. This is the third index that I previously told you to ignore. Now it's time to not ignore it. While L and M tell you what is the angular pattern of the modes around the black hole, N tells you about the radial pattern, where the black holes, where the modes are concentrated around the black hole. And you can see that as you change N from 0, 1, 2, 3, what happens is the frequency of the mode doesn't change too much. What rapidly changes is the damping rate. So the modes will look something like this. If the fundamental N equals 0 is the blue, the N equals 1 will have a much higher damping, and it will look like the yellow. We call that an overtone, which is a bad name because typically overtone means higher frequency. That's not what it means for us. It means almost the same frequency, but higher damping rate. Bad name, I know, sorry. So with this context of modes, there's two big ideas that we are interested in. The first is something called the no-hair theorem that tells you that black holes are only characterized by their mass and their spin. So this pattern of modes that I'm showing you here only depends on the mass and the spin of a black hole. By the way, the no-hair theorem, because of its name, has given rise to decades of really bad jokes in the field about going bald and whatever. We're not gonna do that here. But the important thing for us is that we can use these frequencies and damping rates of black holes to do a spectroscopy test. And that is your standard spectroscopy test that you know from other contexts. You measure frequencies and damping rates, and they must, if this is a Kerr black hole that created those, the frequency and damping rates must be agreeing with the spectrum of some Kerr black hole with some mass and spin, which means that if you measure enough of those modes, you can do a consistency test. You can ensure that the frequencies and damping rate you have measured can indeed come from a Kerr black hole. That's a spectroscopy test that you can do and that we did with this loud signal that we talked about, that we're going to be talking about. Okay, so the overtones are basically what you need to detect. You can always detect a fundamental mode, that's easy. The difficult thing is to detect the overtones. And people have been trying to understand how to find the overtones for the last 10 years quite rigorously. Basically, because we have numerical simulations, we have all the simulations of black hole mergers we're talking about, you can go to the simulations and figure out if the simulations agree with a number of overtones. So what this plot here shows you, I want to give you a brief idea of what this kind of business looks like to understand the theoretical underpinning of the measurement. So the x-axis here is time, where 0 means the merger of the two black holes. So if I pull the signal, 0 is sort of the merger. And you're looking at what happens here at the very late stages of the signal, and you're trying to describe the signal with these modes, with these quasi-normal modes. And the different lines use more and more of these modes. So you use 0 is just the fundamental 1, 2, 3, you keep adding lines. And the y-axis tells you how well you have fitted the signal. So the more of these modes you use, the better you fit the signal, your mismatch goes down, and the further you can go back in time. Then the further you go back in time means the merger of the two black holes. So if I only have one mode, I can understand the signal out here. If I have two modes, maybe I can understand a little bit further back. If I have three modes, a little bit further and further back. So that's sort of the general observation in the field, which has given rise to a lot of debate of whether this makes any sense. Because we're doing first order perturbation theory here, remember? This is first order perturbation theory with which we're trying to understand two black holes that are merging. Does this picture make sense? Does it not make sense? This is subject to a big theoretical debate that I don't really want to go into. I'd be happy to discuss it more. However, I want to briefly mention it just for context. Basically, the problem is the following. I really like this plot because it shows you, it's complicated, so give me 1 second. But I think this plot really shows you what the problem is, why people are so sometimes upset about these modes. So this is a function of time here. 0 is again the merger. And the gray line is one of these simulations, these numerical simulations that describe the signal perfectly, remember. And if you try to understand this signal with a number of modes, if you sum a number of modes, you can do it almost perfectly. Compare the gray solid with a white dashed. You understand it perfectly. This is the agreement is amazing, right? So what went into it? Those 4 different modes went into it. And I'm showing the modes here as well. This is not great. You are summing things that are very large, that they're almost distractively interfering with each other to get something of order 1. This is sort of the kind of the hang-up, the theoretical hang-up in the field. Basically that overtones, these kind of modes, they do come from perturbation theory. They exist in the system. However, are we really pushing perturbation theory really beyond where we should be pushing it if we're applying those fits and the solutions for perturbation theory all the way back to 0. 0 means the merger. So this is sort of a big theoretical debate in the last 10 years in the field, which, full disclosure, we're not going to solve theoretical debates from the data. We're going to solve them from numerical simulations. However, from the data, that gives us a little bit of guidance of where our sort of fits and the QNMs are safe to use. So if you are all the way back at 0, the merger of two black holes, I don't know, people are getting concerned. If you go a little bit further away from the merger of the two black holes, perturbation theory applies more. So with this context, let's go and look at the data. I'm going to skip this and go and look at some data. So the first time we tried to do this, of course, GW15914, the very first detection, tried to model it with perturbation theory. And the answer is the following. Again, remember, 0 means here the merger. So you only see the late stages of the signal. And in this case, blue is the fundamental mode. It's always there. It's there at late times. You see the blue here is always there. And pink is the overtone, the second mode that you want to detect. And the result in this case was that we have a tentative detection because the uncertainty in the pink is large. That's why I mean tentative detection of a second mode. But in order to do that, you need to go all the way back to 0. So all the way to when the black holes merge, which means that this kind of measurement, while interesting, it is subject to all the theoretical debates and caveats about whether perturbation theory makes sense when two black holes merge. What the new signal affords to us is that we can do the exact same thing without worrying about theoretical concerns, because we can do the exact same thing pretty far from the merger. And in this case, this is far enough that the theoretical debate is less of a concern. So here I'm showing the new signal, 250114. The white is the total signal, and we are decomposing the total signal as detecting different modes to understand it. Yellow is the total, is the sum of two modes. Blue is the fundamental, and pink is the overtone. So now, not only can we detect the signal pretty definitively, the detection is very clear, but importantly, we do it far away from the merger. And for far away, I mean 6 times the mass of the black hole converted into time, away from 0 when the black holes merge, thus bypassing the theoretical uncertainties you had about whether perturbation theory applies exactly when two black holes merge. This is what the new signal allows us to do this test without having to use data from the time the two black holes merge. We can also show more convincingly that the detection is robust by also looking at consistency. So the top plot here shows you the amplitude of the fundamental mode. This is the 2-2-0 mode. And the bottom shows you the amplitude of the overtone, the 2-2-1. You see that the overtone decays much more rapidly than the fundamental. And the important thing to note here is not so much the different measurements. Those are measurements you make at different times as you analyze different amounts of data. The important thing to note here is this gray line. This gray shading here essentially tells you how you expect the modes to decay. You have because if these are Kerr black holes, you know how the modes are supposed to decay. You know what the damping rate is. And this is the gray shading here, tells you how the modes are expected to decay. And then you go in at different times, measure the amplitude of the modes, and you get those measurements, either the green or the yellow. I'm not going to go into details about the difference, but there are different ways to measure them. And you see that your measurements agree with the theoretical expectation for how the black hole, the modes decay, which gives us more and more confidence that these are indeed the two modes that we are detecting. They're decaying the way we expect them. So at late times out here, we have the fundamental mode decaying consistently with expectations. At earlier times out here, we have also the first overtone decaying again as expected from theoretical expectations. So we're fairly confident that this picture makes sense. This is a robust detection of the second mode. And if we have a robust detection of the second mode, we can go and do spectroscopy, test the no-hair theorem. So what you do in this case, you allow for a deviation in the frequency and the damping rate. In this case, you have the frequency of the overtone and the damping rate of the overtone. Those are equal to the Kerr value, the value you expect in general relativity, plus, or in this case, times a correction. And if general relativity is correct, then this correction needs to be 0. You go and measure it from the data, and you get indeed that this correction is consistent with 0. The plot on the left shows you the frequency of the overtone, the frequency of the fundamental. This is your measurement when you don't assume that those are Kerr black holes. This is the expectation if they are Kerr black holes and they are consistent. On the right here, you also have a direct distribution from the deviation. It's consistent with 0, which means that those are very consistent. The spectrum of the black holes that we're detecting is very consistent with a spectrum of a Kerr black hole that was created after the merger of the two initial black holes. By the way, before I move on to the second test, I want to quickly reveal a small Easter egg in the that we managed to put in the paper. So if you notice the 0 here, 0 means this is a Kerr value. This is what you get if you have a Kerr black hole. And if you notice this vertical line that denotes the Kerr value, its style is not one of the standard styles that you have in MATLAB. It's not dotted, it's not dashed, it's not dot dashed. Instead, what it is, it's Morse code for Kerr. We managed to put this little Easter egg in the paper, and we're very, very proud we've managed to push it through the collaborations review process, which is not known for its sense of humor. Okay, so this is the spectroscopy test of black holes. The frequencies of the modes that we detected match the Kerr spectrum. Okay, that was the first test. I quickly want to mention a second test that we can do with the same signal, and this is something known as the second law of black hole mechanics. That's also known as Hawking's area law, that tells you that the event horizon of a black hole, or two black holes in this case, cannot decrease with time. What this means in a binary is that if you have two black holes that are merging to give rise to a final black hole, the area of the initial black holes, or the sum of the area of the initial black holes, needs to be smaller than the area of the final black hole. The area of a black hole horizon must always increase, which kind of puts a limit on how much energy can be emitted in gravitational waves. You cannot have a situation where two black holes come together, merge, and lose so much energy that they completely evaporate and you have nothing left behind. This is not allowed. Instead, your gravitational wave efficiency needs to be limited to about 30%. In reality, the signals that we're detecting have an efficiency of about 5 to 10%. 5 to 10% of the mass of the system is emitted in energy. So they're pretty good emitters in terms of, other emitters out there, but still they don't saturate the 29% limit. So this means that this test is a weak test. It's not a very strong test, but it's a fundamental property of black holes that we can go and test with this signal. Okay, so basically, what we are trying to measure is the surface area of the event horizon of two black holes. The surface area of most objects are something like the mass squared of the object, because the mass is proportional to the radius. So at first glance, you might be thinking that if you take two masses, you merge them, you add them, obviously the surface area is going to increase, right? This is a trivial change. What makes this a non-trivial statement is that obviously, first of all, energy is emitted in gravitational waves. So one of the things we're testing is that the black holes did not lose too much energy. And the second thing that we're testing is what happens with the spin of a black hole. If a black hole starts spinning very rapidly, its area decreases quite dramatically. You can see the dependence here where chi is the spin of the black hole. As you increase the spin, the area really goes down. So we're also testing that the final black hole is not spinning too rapidly. Otherwise, it would violate the area theorem. Okay, so if we have some data and we want to test this theorem, we take our gravitational wave signal. It looks sort of like this. We only look at the late stages when you have a final black hole after the two black holes merge. So we only use the shaded yellow part here to measure the area of the final black hole through the quasinormal mode framework I just described. And then if we want to look at the initial, the area of the initial black holes, we only look at what happens before merge, so before the black holes merge. So for example, the blue part of the signal. For context, if you're wondering why we stopped there, because this is where you get about 10% of the peak luminosity of the signal. The luminosity, so how much energy you're emitting as a function of time, really peaks during merger. It peaks really sharply around here. So the previous stages where the black holes are just going around each other, the luminosity is not very high, which means the system is not very relativistic. So this is why we pick this line. It's about 10%. So if you do this test, you get a measurement of the area difference between the final black holes and the initial black holes. 0 is here. If we were on the left of this line, we would be violating the area theorem, but we are happily on the right of this line. The pink is our measurement. So it is not violating the theorem. The area of the black hole did increase during the merger. And we do this basically, remember, by excluding 2 cycles here, the 2 loudest cycles during the merger, measure the area at the end, measure the area at the beginning, take the difference. And the answer is that the area increases to very high confidence. In this case, we put a number of something like 4.4 sigma significance, but once you're at 4 sigma, it's almost the same as infinity. Okay, so these are the 2 tests of the fundamental properties of black holes I wanted to talk about that we were able to do with this signal that we got after the detectors underwent basically a decade of improvements to give us something as clear, as loud. Before I conclude, I quickly want to mention next steps. We've been going through this 4 observing runs. All the data has been collected, and we will be, right now the detectors are offline, but we have recently decided we will resume observations by around the middle of 2026, around September 2026. There's going to be another short run. And the detectors will, however, have basically the same sensitivity as they had when they went offline back in November. So we expect to keep observing something like 1 black hole binary every 3 days or so, which at this stage, at the same time, gives us more and more information about the astrophysical properties, demographics of black holes, or it might allow us to observe another extremely loud signal like the one I just described and get more information about the fundamental properties of black holes. So with that, I want to stop here and take any other questions. Thank you.
Thank you, Katerina, for this great talk. Questions, Yoni?
So I'm going to ask you a question that I think I asked you a couple years ago, but now I want to know with all this new data how your thinking might have changed. So it seems like gravitational waves is in a very similar situation to what particle physics was like before the LHC turned on, with possibly correctly tempered expectations for what you might see as, beyond GR. For us, it was, beyond the standard model. So, fast forwards, the LHC has been on for, more than a decade and a half, and we've now confirmed the standard model at 5 sigma in like n different channels. So you're not there yet, but let's assume that's what happens during 05 or something. Like every check you've done of GR, it just passes at 5 sigma. What is the most interesting physics you can get out of like seeing 1 black hole merger a day? Like where's the most interesting analysis you can imagine performing in a situation like that?
So I sort of agree with the spirit of your question in that the answer is not much. Those signals that you keep observing in high rates are not telling you so much more about the fundamental properties of black holes. They're telling you more about the demographics, the astrophysical properties. Now, I wouldn't say this is a fully accepted view, but in my view, the moment you see this merger and you do some rough estimates that it agrees with general relativity, that's it, right? You're not going to detect quantum gravity here, way off in energy scales, length scales. You're not going to do that. What you can do is get some rough estimates that these look like the black holes you expect general relativity, measure some of their properties. The merger looks like this, not a complete mess compared to what general relativity predicts. Now, beyond that, I think that is the extent of where this is going. If you have a louder signal, what it will allow you to push things further. It will allow you, for example, to detect a 3rd mode in the spectrum, or detect a 4th mode and get more and more consistency tests, get the spectrum better. But it's not the detect a new particle type of situation. You get better and better constraints on the spectrum of black holes, But I would say to a large extent, the fact that seeing one signal, seeing that this agrees, it agrees. You're not going to get quantum gravity here. So I don't know if that is sort of similar LHC. You need to go 10 orders of magnitude more to get anything. Yeah.
Thank you for the great talk. So what changes were made to the detector that improved the SNR that much?
Oh, lots, tons of changes. So for this range that we're talking about, I go back. So each of these steps include a large number of changes. You can maybe see that between here and here, the changes didn't improve things too much. The large changes happen from here to here and from here to here. So these include things in basically trying to isolate the detector better, trying to beat out any environmental effect, any noise coming from environmental impact around the detector, mitigating any anthropogenic disturbances, anything that happens of this front, but also trying to beat down fundamental quantum noise levels. All these all these processes are happening simultaneously. One of the big improvements from here to here, for example, is introduce the detector something called squeezing, frequency-dependent squeezing, that allows you to essentially alter the vacuum state of the light that you put in the detector. And that gave you a lot of the improvement here. But it's not all quantum precision measurement. There's also a lot of work to beat down the anthropogenic noise and isolate the detector, and also a lot of trial and error, try to isolate the detector, see what works. So a lot of effort.
Would it be possible or useful to go beyond first order perturbation theory? And
Yeah.
could you do it?
Yeah, people are doing it. People are doing this calculation. It's not an easy calculation.
Yeah.
And they haven't completed it, to my knowledge. However, what happens in second order perturbation theory is typically waves are sourcing waves, right?
Oh,
so
yeah.
to first order, you have waves, you have the Q and Ms.
And then you get self-interaction.
So these go to the source in the second order. So the solution there, your, say, left-hand side, the operator does not change. So the solution is still quasinormal modes that are sourced by quasinormal modes. So what changes is basically the frequencies. They still look like quasinormal modes. Where things become interesting is in third order perturbation theory, because that's when you get back reaction of the waves sort of falling into the black hole and changing the mass and spin of the black hole. So actually where people try to go is third order, not so much second order. Second order is kind of boring. Third order is where the exciting things happen.
Thanks for the really interesting talk. I wanted to ask two quick questions. First of all, I noticed there's the event in run 2 that was much closer to us. Is there anything interesting to say about that? And then my second.
The neutral star binary.
Okay.
If you extend the scale to include it, it would break. It would break the schematic. It would look very ugly. So instead, we decided to say just put it like this. But this is the neutral star binary. It happened very close by.
Okay, thank you. And then also for the event that had a very strong signal that we were talking about, is that signal attributed only to changes in the detector, or are there also special things about this event that led it to have a stronger signal?
No, it looks very similar. The source that created is very similar to other sources we've seen in the past. It was very similar to the first one. It was very similar to this one. The masses, the distance were very similar. The main difference is the detector improvement. Mm-hmm.
Thank you for a great talk. So I was wondering about the later part of the talk that you're mentioning of like fitting the end of the signal, like the first overtune, the second overtune. So for someone who's not in like astronomy, that's just like a Fourier transform or Fourier series, like composition. So why does it trigger so much debate, or like what does the debate come from?
I would say the debate is the following. Yes, you can fit a signal with something, but quasi-normal modes is sort of the solution to everything. Everything is a decaying sinusoid, right? It's not a very unique template. It's not. If your solution to the solution to your problem is this is a very unique type of signal. If you see this, you know what it is, right? But if the solution to your problem is just a decaying sinusoid like this part, there are a lot of things that cause decaying sinusoids all over the place. That's mostly what the problem is. Like your equations give you the solution, but it's not clear that you're not just fitting anything because they're dumb sinusoids. You can fit anything with them.
Can you tell me where KAGRA is? And I noticed it came into play in the fourth segment. And how has it incremented your information about the black hole mergers?
Yeah. So besides the two LIGO detectors that made the observations I was talking about today, there's also two partner detectors. One is Virgo in Europe that has a sensitivity about 5 times worse than LIGO. However, it is contributing and making detections. And another one is Kagra, what you're referring to, which is in Japan, which joined us in observing in the 4th observing run. However, it did not have the sensitivity to meaningfully contribute to these. It's still undergoing the stages of improvement that we're talking about, that LIGO has had a long history on. It's still undergoing those changes to improve. There's more ideas for further detectors. There's one in India under construction right now that should be coming online some like 4 years, early 2030s or so. So there's other detectors. However, the two LIGO ones are the most sensitive right now.
I see no more questions. Then let's thank Katerina again for the great talk.